Hi, welcome to lecture number 10, derivative rules. I drew one of the rules down here. I think after watching this video, you should come back to this screen here and try to figure out which one this rule is. All right, so just as a reminder, the last lecture that we had that wasn't a review, it was about the derivatives, but actually the definition of a derivative. So I have rewritten that in here. The derivative of a function f at a point A, by definition, it's this number that you can denote by f prime of A or df dx of A. It's a limit that can be computed in two equivalent ways. Either you take a limit variable to the number A and you do this form of the difference quotient right here, f of y minus f of A over y minus A, or you do a limit variable going to 0 and you use this form, f of A plus h minus f of A over h. That's a number, that's f prime of A, so whenever this limit exists. And we can also talk about the derivative function, the function f prime or df dx is by definition, it's the same thing really. It's just this limit evaluated at every possible point x where this limit exists. So now we're thinking of this x as a variable instead of a fixed number a, but you can see that it's exactly the same thing. All right, so this is the notion of a derivative, and we have computed a few of them last time by using this definition, but I had also mentioned that we basically never do that. There are practical rules that help you to do this calculation without having to compute a limit. That's the goal for today. Goal for today is practical rules to compute derivatives without having to compute a limit. And more specifically, we're going to be looking at the derivative of specific functions like polynomials x to the r, exponentials e to the x, logarithms in any base, actually not just ln, trig functions, sine, cosine, and everything that you can form from those like tangent, cotangent. And we're also going to look at the rules for what happens to the derivative when you start combining these functions, like one plus the other, one minus the other, or multiplying by a constant, or multiplying two functions together, dividing two functions together. There are derivative rules that tell you how to compute the derivative of these expressions. We're going to be looking at that. The first one that I'm going to mention is this one called the power rule. So you're looking now at a function where the variable is in the base. It's x, the variable x raised to a constant r. So for any real number r, the derivative of this expression is r times x to the r minus 1. What does that mean? It means if f of x is equal to the function x to the r with the appropriate domain, we'll talk about that later, then the derivative function f prime is r times x to the r minus 1, also with the appropriate domain. Think of it this way now, the original exponent r actually drops down in front of the expression. You see that the r is now in front, and the exponent, which was r for the original function, now is r minus 1, so it's the original minus 1. If you want to, some help remembering this formula. So here are a few examples where r is an integer positive number. The derivative of x to the 5 is 5 times x to the 4th. And the domain here would actually be any x. These expressions make sense for any x. The derivative of x squared, 2x times, if you want to think about it, the exponent, which was originally 2, should now be 1, but x to the 1 is just x. That's how I got the number 2x for the answer. Let me draw this 1 here a little bit better. So the derivative of x squared is 2x. The derivative of x is 1. How does that happen? The function x, it is x raised to something. It is x raised to 1. So if you want to find the derivative of that, you can use this power rule. It would be 1 times x to the 0. But x to the 0 is just 1. So the derivative of x is 1. And I wrote a remark here that this actually makes sense. Think of the graph. The graph of the x function is this line at a 45-degree angle, actually extending at any value of x. We know that the derivative is the slope of the tangent line. Well, the tangent line to this graph is the line itself, is the graph itself, and it has a slope of 1 because of the 45-degree angle. Tangent of 45 is 1. So it makes sense that the derivative at any point is always the number 1. Finally, c, a constant, a number c, the derivative of that is always 0. Derivative of a number is 0. How does this follow from the power rule? If you have a function that's constant equal to c, well, c is x to the 0 times c, I guess, because x to the 0 is 1. So again, you can try to argue the same way. I mean, at least once we know what happens when you multiply a function by a constant, but we're going to talk about that very soon. So this rule also implies that the derivative of a constant is 0. Essentially, the 0 from the power is going to drop down in front, and that makes a 0. Again, the same remark here. This makes sense. Think about the graph. The graph of a constant function is a horizontal line wherever that constant is. And the slope of this line is 0 everywhere. So these were some very simple examples. But now I have some also simple but slightly more complicated with negative powers. Calculate the derivative of each one of these guys, and now state for which x's the formulas are valid. So if f of x is x to the minus 2, f prime is going to be minus 2 x to the minus 2 minus 1. Always like this for the power rule, which becomes minus 2x to the minus 3. Or if you want to rewrite this, remember that negative power is the same thing as dividing by the positive power. So what is the domain for this expression? It would be different from 0. The formula for this derivative makes sense for all x's which are not 0, because there is an x in the denominator. So that's the derivative of x to the minus 2. Now this g of x here, 1 over x, looking at it, you don't see immediately that this is x raised to something. If you want to use the power rule, you have to have x raised to something. But it actually is true. G is x to the minus 1. 1 over x is x to the minus 1. So once you know that, you know g prime. G prime is minus 1, x to the minus 1 minus 1, or minus 2. Which is also minus 1 over x squared, again for x different from 0. Finally, the last one, 1 over x to the 7. First, you have to rewrite the function as x to the minus 7. That's what the function is. Then you can say that the derivative, according to the power rule, minus 7x to the minus 8. How did I get minus 8? It's the original exponent minus 1. That's always the case. And you might also want to rewrite this function as minus 7 over 8. Once again, the domain is x different from 0 for these guys. That's always what happens when you have a negative but integer power. As long as x is not 0, then the expressions make sense. Now let's do some examples involving non-integer powers, but they're very similar. Calculate the derivatives, state for which x the formulas are valid. The first one, they have a power of 7/3. Let me already compute the derivative. F prime is going to be 7/3 x to the 7/3 minus 1. So it's just a little annoying calculating. It's a subtraction right here with a fraction. You have to find a common denominator, but 7/3 minus 1 is 4/3. This is what you get. And the domain, when you're raising a number to a non-integer power like this, usually you only want to do that for positive or possibly negative or possibly 0x, but not negative values. The reason is, I mean, this power, it would be okay with a 1/3, but if you're raising to something that involves a even denominator like 1/2, denominator like the number 1/2 here. This is the same thing as square root. Now we know that you cannot take a square root of a negative number. So for that reason, even when it's an odd denominator, usually the domain for the expression is considered to be only positive x's. And in this case, it could also be 0 because we are not dividing by 0 in this expression. This expression can be calculated at x equals 0. So that's really the only thing that changes about non-integer powers, fractional powers. The domain does not have negative numbers. Now g of x, square root of x. That's not written in a form of x raised to a power, but we can do that. Square root is the same thing as x to the 1/2. And once you've done that, the derivative is easy to find. 1/2 x to the 1/2 minus 1, which is the same thing as minus 1/2. So you might want to write this in this form. You have 1/2 in front times x to the minus 1/2 is the same thing as 1 over x to the 1/2, which is square root of x. So the derivative of square root is 1 over 2 root x. I think we have computed this before by directly computing the limit, and now we can find it much more easily. The domain for this expression is positive x only. Because now that you have an x in the denominator, it cannot be positive. It cannot be 0. Sorry. The last one, h. H is 1 over the 4th root. That's the same thing as raising to minus 1 over 4. 1 over 4 for the root, and minus because it's in the denominator. So the derivative will be minus 1 over 4, x to the minus 1 over 4 minus 1, which is minus 5 over 4. So now there are many ways to write this expression. You could say, for example, minus 1 over 4 times 1 over 4th root of x to the 5. But unless there's a reason to simplify it like this, you probably want to leave the answer in this primary form here. That's already enough. The domain is also x positive for the same reason as above. So yeah, just this remark right here. What is the domain of x to the r? We have already discussed this. If r is integer, then you just care about 0 or being included or not in the domain. If r is positive, then you're not dividing by 0, so you can include 0. If r is negative, you cannot include 0 in the domain. However, if r is non-integer, the domain is considered by default to not have negative numbers. And it could be from 0 onwards, including 0 or excluding 0, depending on the sign of r. So we should just remember this if we are ever asked about the domain. And a quick remark here about how you would prove this formula, the power rule. We already proved it last time for positive and integer r. It was called n, actually, in the example that I gave in a previous lecture. We calculated the limit with this function, and we've seen the formula showing up. Now, if r is integer but negative, you can also calculate that. It's really not that hard. So the only cases that are actually left to prove is when r is non-integer. But the remark that I have here, we're not going to prove this. The remark is, first of all, it requires being able to even define what the function is, x to the r. What do we mean by raising a number to a fractional power? What does that mean? So if you ever do a course in real analysis where you actually want to prove results formally, rigorously, this is the path that you need to take. First of all, actually defining this function and then computing its derivative using the limit. I just wanted to mention this. But we should not be focusing on that. We want to focus on the rules and their practical application. Next rules that I'm going to mention are the linearity rules, and these are really easy. As long as you have two functions f and g which are differentiable, then let's look at the second one first here. The derivative of the sum or difference of two functions is the sum or difference of the derivatives. Exactly as you would expect. And if c is a constant, the derivative of a constant times a function is the constant times the derivative. You can think of this as the constant jumps out of the derivative, unharmed. So for example, 7x to the fourth, what is the derivative? 7 is a constant multiplying the function x to the fourth. So we can bring the 7 outside of the derivative operation. And then we just compute this derivative. X to the fourth becomes 4 times x to the 3. And then 7 times 4 is 28. So this is a very easy calculation right here. And the next example here is a difference between two functions. Each one of them has a constant in front, like the 2 and the 5. So when you want to differentiate this expression, you can rewrite it this way. The 2 comes outside of this derivative for the function cube root of x. Then there's the minus sign. Then the 5 outside of the 1 over x squared. So you see that this was a combination of both rules. I also distributed the derivative inside of each term being subtracted right here. Now we just have to compute this. Instead of writing cube root of x, I'm going to write x to the 1/3. Instead of writing 1 over x squared, I'm going to write x to the minus 2. So that now we can apply the power rule. The derivative of x to the 1/3 is 1/3 x to the 1/3 minus 1. And the derivative of x to the minus 2 is minus 2 x to the minus 2 minus 1. That's the power rule. Let's just simplify this now. 2 times 1/3, 2/3. X to the 1/3 minus 1 is minus 2/3. Now minus 5 times minus 2 is plus 10. And this is x to the minus 3. So this is a perfectly fine answer. You might also want to rewrite, for example, like this. X to the 2/3 would have been cube root of x squared. But because we have a minus sign in the exponent, it's actually 1 over that. And then x to the minus 3 is just 1 over x to the 3. This is another way to write the expression, but you don't have to. Sometimes it's useful if you're trying to simplify, if you're trying to apply this to some other calculation. But if nobody says anything, you can also leave it this way. So as I said, those were easy formulas. These guys right here, I'm just going to mention. We'll have a few examples involving them later, but we should remember these. The exponential function e to the x, its derivative is itself, e to the x. And the domain is everything because, well, e to the x is defined for all x's. And the natural logarithm, ln, its derivative is 1 over x. The domain is only positive x's. It has to be only positive because ln of x is only defined for positive numbers, even though this 1 over x is defined for negatives, but the original function already was not defined on the negative. So the domain of this formula is positive numbers. All right, now we actually considered an example in a previous class where we were looking at these functions graphically and we were trying to at least draw the graphs of the derivatives. You may remember this. We basically said the graph of the exponential function looks like this. And because of that, its derivative kind of also looks like the same if you're considering the slopes of tangent lines. So we know that the graph of the derivative looks like that as well. Now I'm just telling you it is the same function. And meanwhile, for ln, here's the graph of ln. We should always remember this one. And we also mentioned if you're trying to graph the derivative based on this graph, you can see that the slopes are always positive but they are larger when x is closer to 0. So the derivative looks like this green graph. Well, that's the graph of 1 over x, actually. I mean, this doesn't prove anything. You have to go through the calculation of the limit if you want to prove this. But I'm just saying that we should at least try to think of it this way. It makes sense. But yeah, let's just remember these guys. We'll be applying them to formulas later. But let's move on to other formulas. The product rule. You should always remember, derivative of the product is not the product of the derivatives. It's not like the sum. So if you're trying to differentiate a function times another, you do not distribute this prime into each function. Rather, you do it like this. F prime times g plus f times g prime. So you're going to have a plus with 2 terms. Each term only has 1 prime, whereas the other function it appears in that term intact without the prime. This is, by the way, also called the Leibniz rule. Leibniz was one of the people who invented calculus back in the 1700s, maybe, or even 1600s. So this is the product rule. We'll see some examples of this. Compute by using the product rule. By the way, notice that I'm using different notation, different variables, just because we should be getting used to this kind of thing as well. ddz, it just means the derivative with respect to z. Z is the variable being differentiated. Rather, the variable with respect to which we are differentiating the function. Okay, so the function is z squared e to the z. It's a product of 2 functions. The derivative of this product, I'm going to apply the product rule. How does that work? You differentiate the first and you multiply by the second function, plus you keep the first function and you differentiate the second. That's the way that the product rule works. Now we just have to compute this, but that's easy. Z squared prime is 2z, power rule, times e to the z. Now z squared times e to the z prime is just e to the z. The derivative of exponential is itself. So that's your answer, or you can also factor like a z and e to the z if you want. 2 plus z. Just if you needed to factor this expression for some reason. That's the derivative. Now the next one, if you think about this, it might have been smarter to first simplify the function. Look at this function, t to the minus 3, t to the 5. If you combine these two, you just have t squared. So the function is actually t squared. We're looking, the answer that we're going to get should be 2 times t. That's the derivative of t squared. But they're asking us to actually use the product rule. So we need to use this form of the function. It's a product of 2 separate pieces, and we want to use the product rule. So we'll do that. T to the minus 3, t to the 5. You need to differentiate the first function, multiply by the second, plus leave the first function and multiply by the derivative of the second. Let's compute this. Minus 3 t to the minus 4 times t to the 5 plus, here's a t to the minus 3. Derivative of t to the 5 is 5t to the 4. That's the power rule. But let's look at what happens here. If we simplify this expression, t to the negative 4 times t to the positive 5 is just t. And here, t to the negative 3 times t to the 4 is also just t. And 5t minus 3t is 2t, as we had guessed before. So it is working. This is how you would use the product rule to differentiate this expression. Here's a question that I often get. I want to get rid of this question right away. Imagine that you have a function 2 to the x, 2 times x to the 3. By the way, first of all, this is not the same as 2x to the 3. That's not what this is. It is rather 2 times x to the 3. I've seen people making this confusion. Don't make this confusion. When you have no parentheses like this and you have a power in the end, the power is only applied to the very last variable. All right, so we have this function. The question is, do we view it as 2 times x to the 3 and use the product rule or not? The answer is it doesn't matter. I'm gonna just show you. So not using product rule, we already know how to differentiate this expression. The 2x cubed prime without using product rule. I had told you already, you can view this as a constant times a function, and the constant can come outside of the function being differentiated. And now you just compute this derivative, 2 times 3x squared. So that's 6x squared. So this is what we already knew, how to differentiate this. But what if you wanted to view this as a product of 2 functions? One of them is the function 2, a constant function, and the other is x cubed. Well, if it is a product, do we have to use the product rule? We don't have to, but we can. That's what I want to get to. If you want to differentiate the product 2 times x cubed, let's use the product rule here. So 2 prime times x cubed plus 2 times x cubed prime. Those are the 2 terms that you get. But you see that the derivative of the first one, this 2 prime, what is that? Let me write this prime carefully. I don't want you to think this is a number 1. This is a prime. It's a derivative. 2 prime is 0. The derivative of a constant is always 0. And what you have left now is the same thing that we just had above. 2 times 3 times x squared. So you see that doesn't matter. The answers should be the same. So the answer here, you can use the product rule if you want, but you shouldn't do that. You should not be confused by this because it's just a constant, the number 2. So it comes outside of the derivative. You should think about it as the first method, not the second. Moving on. Quotient rule. This is kind of a big formula. Again, it's important. We need to remember this always. The derivative of the quotient is not the quotient of the derivatives. It actually works like this. If you have to differentiate f over g, this is the answer. And there's a mnemonic that people use, the thing that you can say to yourself to remember. It's like low d high minus high d low over low squared, where high and low mean f and g. If you look in the fraction here, so low d high is this first term here. G times d high is derivative of the high function, so f prime. High d low is f times derivative of g. Low square is g squared. So just try to remember it this way if you want. And when is this formula valid? It's valid as long as both f and g are differentiable, and g of x is different from 0 because there is a g or g squared in the denominator. That's the domain for this formula. So this is how you compute derivatives of quotients. Let's put this into practice. Compute by using the quotient rule. So yeah, those are 3 fractions. Let's go ahead in the first one. X squared minus root x over ln x. Well, I'm gonna just write low d high. So d high is the derivative of the numerator, which is x squared minus root x. Now minus high d low. Don't forget the parentheses here. The high function, the numerator, is 2 terms. And that function entirely must be multiplied by the derivative of the denominator. So we need this parenthesis. The whole thing is divided by ln square, low squared. Okay, now we need to compute these derivatives right here. X squared derivative is 2x. Square root of x, first of all, minus sign. Now, square root of x, remember that the derivative of square root of x can be found by writing x to the 1/2. So let me circle this in another color and compute that separately up here. The root of x prime is the same thing as x to the 1/2 prime. We've done this using the power rule and then rewriting this expression. That's a derivative that you're going to end up memorizing. Derivative of square root of x is 1/2 times square root of x, found by the power rule. So that's what we have here, minus x squared minus root x. ln x is one of those that I mentioned. We just need to remember the formula. Ln x prime is always 1/x. The whole thing is divided by ln x squared. Probably not worth simplifying anything in here. I mean, one thing that can be done, this 1/x distributed with the x squared will use a simplification, but we don't have to. This is the derivative. And they're not even asking for the domain here. It's kind of messy. So let's not worry about it. Let's move on to the other examples. We have 1/y to the 6 prime. Well, this is one that you can do by the power rule. If you just rewrite this as y to the -6, you can use the power rule. But they wanted us to use the quotient rule, so we're going to do that. Low g high minus high g low over low square. That's what you get. But then here, the 1 prime is a 0. This term, the first term here disappears. 1 prime is 0. So what you have is minus 1 times, what is y6 prime? That's 6 times y to the 5. This is just the power rule once again. And downstairs, please don't tell me this is y to the 8. It's actually y to the 12. When you have powers of powers, you multiply the powers. So 6 times 2 is 12. This you can simplify. You have y to the 5 in the top, y to the 12 downstairs. This leaves a y to the 7 downstairs. This is exactly what you would get from the power rule. And finally, the last one was z times e to the minus z. Prime. Well, keep in mind, they said use the quotient rule. If this is right here, right now, this is a power. We're multiplying two functions. And we actually don't know how to differentiate e to the minus z yet. We know e to the z, you know, the exponential function, but not with a minus sign. So, but because they said use the quotient rule, we need to first of all convert this function into a quotient. And the easiest way here is to do this. Instead of writing e to the minus z, I'm going to write 1 over e to the z. That's the same thing. Now this is a quotient, and now we can use the quotient rule. Low d high minus high d low divided by low square. Now computing this, the variable being differentiated is the z variable this time. Z prime is 1. Okay, this is just the power rule once again. Z to the 1 being differentiated. Now in the second term, e to the z prime is just e to the z. And downstairs you have e to the 2z. If you factor in e to the z from the numerator, you can simplify this. You're going to be left with only 1 e to the z in the denominator. You should simplify because it's easy enough to do in this case. But that's your answer. I have a couple quick remarks now about proving these formulas, I'm just gonna go them quickly. Once again, we don't have to worry about this, but you should at least try to understand what's going on. You should not think of these formulas as magic coming from out of the hat. They are simply, I mean, they come from somewhere, and they come from the definition of the derivative. So for example, imagine that you're trying to prove that the derivative of e to the x is e to the x. So you have the function e to the x. Computing the derivative f prime, by definition, let's use the form of the limit that has an h going to 0. This is what the derivative at the number x is supposed to be. Now I'm going to write e to the whatever instead of f of the whatever. So e to the x here, e to the x plus h in the first term. This is a limit that you have to compute now. One simple thing that you can do is factor e to the x, which I'm doing right here. And in fact, the limit variable is the h variable. X is just a constant with respect to that limit, so we can even write this e to the x outside of the limit, leaving e to the h inside, and just 1 for the second term. So now you have e to the x times a limit. And this is a point where you basically stop. This limit is equal to 1, but I'm remarking it down here that this last limit is actually not very manageable. Just trying to think about it. It's indeterminate, but there isn't much simplification that you can do here. There is an exponential in the top, but not in the bottom. This is not an easy limit, but however, depending on what your definitions are, your theorems, this limit can actually be viewed as the definition of the number e. This mysterious constant e, this is a way to define it. You can say it is the constant that makes this particular limit equal to 1. In which case, this limit is true by default, okay? So this is, I guess it's not really satisfying, but that's just how this works. If you ever take a course in real analysis, 311 at Rutgers, then you actually have a proper definition of this function e to the x, and you can actually prove that this limit right here is true. Then what's left is just e to the x for the derivative. This is why the derivative of e to the x is e to the x. For ln, I have only 2 lines. I'm saying here, it actually requires the so-called chain rule, which we're going to learn next time. And it's going to be applied to the fact that ln is the inverse function of e to the x. Differentiating an inverse function requires the chain rule. So we can't really prove the formula for the derivative at this point. We just have to accept it. But I'm pretty sure that most of you are ready to accept this without proof. For product and quotient rules, both of them they follow from the definitions once again, using the definition. And then actually the quotient rule follows from the product rule. This can be found in the book if you're curious. I just actually want to leave you with this food for thought right here. I'm not going to say anything about it, but just think about this. We know that the limit of a product is the product of the limits. And we also know that the derivative is a type of limit by definition. So why is the derivative of a product not the product of the derivatives? I think this is an excellent question. Try to consider this if you want. But I will not mention any more words about proving things. We have to keep moving. We're almost done, actually. These two right here, again, you should accept. You should take this, just memorize them. Derivative of sine is cosine. Derivative of cosine is minus sine. A lot of people will make mistakes with the plus and the minus here, the signs. Try not to, it's important. I once again have a remark about how we would prove these guys. Again, it's not an easy computation. Let's not worry about that. Just try to remember the derivatives of sine and cosine. And other trig functions. So I'm writing down the 6 trig functions here that we should all know. Using the derivatives of sine and cosine, which are repeated here for your convenience, and the quotient rule, we can find the derivative of all the others: secant, tangent, cosecant, and cotangent. Because because of this, by definition, secant is 1 over cosine. Tangent is sine over cosine. Cosecant is 1 over sine. Cotangent is cosine over sine. All of these guys are quotients involving sines and cosines. So if you know sine and cosine prime, you know all of those. Now you should probably memorize the second line here, the derivatives of secant and tangent. You're gonna end up memorizing these guys. They come up a lot. To be honest with you, I never memorized the last ones. I don't need to because we can find them using the quotient rules. So just as a quick example, let's find the derivative of cotangent. Let's apply the quotient rule here. Cotangent is cosine over sine. Applying the quotient rule to differentiate this, low d high minus high d low over low square. Now in the numerator, you have cosine prime, which is minus sine. And then minus cosine times sine prime is plus cosine. This is what I'm talking about, the remembering your pluses and minuses correctly. But once we've done all this, you see that the first term is a minus sine square. The second term is a minus cosine square. And this can be simplified because what you have in the numerator here is minus 1 times sine square plus cosine square, which is 1. So the final result is minus 1 over sine square of x. Well, 1 over sine is the same thing as cosecant. So this is minus cosecant squared. Just like the formula told us. So again, if you can memorize them, that's great. If you want to memorize really the ones that you're going to need, it's the first 4. Last slide. These are, again, just formulas for us to remember right now. Derivatives of exponential and logarithm functions in other bases. If you have a function that's a number to the x, b to the x, the derivative of that is ln of b times b to the x. And if you have a logarithm with base b and you want to differentiate that, the answer is 1 over ln of b times x. So for example, we know e to the x prime, according to this formula right here, it should be ln of e times e to the x, which is true because ln of e is 1. So this is really just e to the x. All right, so this formula generalizes the derivative of the exponential function to different bases, like 2 to the x, for example. And similarly for the log in base, the log with ln is the same as base e. So this ln of e that would be downstairs here would simplify to just 1. So that's why the derivative of ln is just 1 over x. This b has to be a positive number for this exponential and this logarithm to be well defined. And the domain of these formulas, for the first one is every real number, for the second one is only numbers larger than 0, just like in the case of ln. So just pay attention to this remark. Don't confuse exponential functions with polynomial functions. B to the x with x to the n. Those are different things. With the location of the variable, the x. In a polynomial function, it's downstairs. In an exponential function, it's upstairs. So the derivative of 2 to the x, that's an exponential function. According to the formula right here is ln of 2 times 2 to the x. It's not what you would get from the power rule, because the power rule is for x raised to something. All right. So now, for example, what is the derivative of e to the pi? Do we use the power rule or the exponential rule, the answer is neither. The derivative of this is 0 because this is a constant. There is no x here. There's no variable. Those are two numbers, e and pi. So it's just 0. And what about x to the x? Well, we'll talk about this later. This is neither again. You cannot use either one of them because you have the variable in both locations, base and exponent. So later for this one, but we should be finishing by now.